The first lecture of Chapter 2. Chapter 2 is on atoms and elements. And so today we're going to talk a little bit about the history of the atom and how the modern view of the atom came about. So first off, I want to point out that you are responsible for learning some aspects of this course on your own. If you look at the chapter study guides, it covers all of the topics that you're responsible for knowing in a given chapter. So if you look at the Chapter 2 study guide, it will tell you all of the things you're responsible for knowing in Chapter 2. A lot of them will be covered during lecture, but not all of them. This is to ensure that you are reading the textbook and studying on your own. So it's not enough just to sit in lecture and listen to them. You need to go and make sure you are solidifying your own understanding by reading through the topics in the textbook. And then, like I said, double check that study guide and make sure that you have covered all of those topics and that you know everything on that study guide. So these are some of them. We will go through these a little bit, like the law of conservation of mass, the law of definite proportions, the law of multiple proportions. We'll go over some of those, as well as a little bit about periodic law in the next lecture. But you're responsible for solidifying your understanding and deepening your understanding on these topics using the textbook. So just in general, make sure you're always looking at the study guide and double checking that you have met all of those learning targets. Okay. Antoine Lavoisier formulated the law of conservation of mass, and it states that in a chemical reaction, matter is neither created or destroyed. In chemistry and in physics and in science in general, we have lots of laws of conservation of things. We have law of conservation of energy, law of conservation of momentum, law of conservation of mass, and it's just saying that whatever it is cannot be created or destroyed because we have a closed system. It can be rearranged, it can be converted, but it cannot, poof out of thin air, and it can't be destroyed. So when a chemical reaction occurs, the total mass of the substances involved in the reaction doesn't change. So whatever mass you have before the reaction is going to be the same as the mass that you will have after the reaction. So here is a visual of that if we add some sodium and some chlorine, and we talked about that in that first lecture, right? Sodium is this soft silvery metal that you can actually cut with a knife, and like I said before, it explodes when you put it in water, which is super fun. And then chlorine is this green poisonous gas, and if you mix them together, you get stuff we put on food, right? Table salt. But if you look at the masses down at the bottom, you'll see that the masses before the reaction are equal to the masses after the reaction. So mass is conserved throughout the reaction. The mass before equals the mass after. So this law is consistent with the idea that matter is composed of small, indestructible particles. And I'm a big Harry Potter fan, and so I always tell people, this is how I know that magic isn't real, right? You can't create or destroy things. Things can't poof out of nowhere, which is a real bummer, but there you have it. So another one, the law of definite proportions. So we have in 1797, a French chemist, Joseph Proust, made an observation of the composition of compounds, and he said the law of definite proportions, which is essentially that in a pure compound, it always has the same elements in the same proportion by mass. And so what this means essentially is that if you think about water, right? Water is H2O, and our molar mass of water is about 18 grams per mole. And in a given water molecule, 2 of those grams are always going to be hydrogen, and 16 of those grams are always going to be oxygen every single time for pure water. If it doesn't have that ratio, then it's not water, it's something else, right? Maybe it's hydrogen peroxide or something like that. But in a pure compound, we always have the same elements, so we always have 2 hydrogens, 1 oxygen, and they are in the same proportion by mass. So the law of definite proportions, sometimes you'll hear it called the law of definite composition. Those are the same things. But so here you go. In water, right, 18 grams of water, we always have 16 grams of oxygen and 2 grams of hydrogen. So we have an oxygen to hydrogen mass ratio of 8.0 or 8 to 1, right? For every 8 grams of oxygen, we have 1 gram of hydrogen. So that's our ratio. So you can do this as a mass ratio. You can also do this as kind of like a mole ratio, right? For every 2 2 atoms of hydrogen, we have 1 atom of oxygen, or for every 2 moles of hydrogen, we have 1 mole of oxygen. But regardless, you're always going to have a ratio, and it's going to be the same no matter how much water you have. The law of multiple proportions states that when one element combines with another element to form more than one compound, right? So this is the key here. More than one compound. That's where we're getting this multiple proportions. And it says the mass ratios of the elements in the compounds are simple whole numbers of each other. So this, my best example for you is, like we were just talking about, water is H2O, and hydrogen peroxide is H2O2. So in both of them, we have hydrogen and we have oxygen, but they can combine in different ratios. So this is the law of multiple proportions. You can have 2 hydrogens and 1 oxygen, or 2 hydrogens and 2 oxygens. But again, they're always in these whole number ratios, right? We don't have like 2 hydrogens are combining with 1.5 oxygen or something silly like that. So that's the law of multiple proportions. Here's another example of it. Carbon dioxide, right? Carbon dioxide is CO2. Carbon monoxide is CO, right? And so you can, so these are in whole number ratios, and you can also find their mass ratios, just like we were doing with hydrogen and oxygen in the previous slides. So if we have, if we do that for carbon dioxide, then we get for every 1 gram of carbon, we have 2.67 grams of oxygen, and in carbon monoxide, for every 1 gram of carbon, we have 1.33 grams. If we take the ratio of these two, 2.67, 1.33, then we are getting a whole number here, okay? So there you are. That is the law of multiple proportions. So John Dalton is one of the first people to theorize about the atom, okay? And so he had 4 different postulates of his atomic theory. And so the first one is that each element is composed of tiny, indestructible particles called atoms. The term atom actually comes from the Greek term atomos, which means indestructible or indivisible. So he said, okay, John Dalton was like, all right, if you take something, like say a piece of paper, and you tear it in half, and then you tear it in half again, and you tear it in half again, and you keep doing that, eventually you've got to get to a point where you can't tear it in half anymore. You've got to get to something that is so small that it can't be torn apart. And this is what he was saying is the atom, something that is tiny, indestructible, and so we're going to call it the atom based on that Greek word atomos. Okay, so that's his first postulate. Second one is that all atoms of a given element have the same mass and other properties that distinguish them from atoms of other elements. So this one, number 2, is not quite true. We'll look at, later in the course or later in the lecture that not all atoms of a given element have the same mass. So this is actually not true, but it was a good starting point. All atoms of a given element have the same number of protons, and that will distinguish them from other elements, but they don't all have the same mass, but it provided a really good starting point. But so this one, number 2, not true. So his third one was that atoms combine in simple whole number ratios to form compounds. This one's true, right? We were just talking about that. Water, hydrogen peroxide, carbon monoxide, carbon dioxide, right? They're always whole number ratios. We're not having 1 atom of one thing combining with 1.5 atoms of something else, right? They're always going to combine 1 to 1 or 1 to 2, 2 to 2, right? Things like that. And then the last one is that atoms of one element cannot change into atoms of another element. In a chemical reaction, atoms only change the way that they are bound together with other atoms. This is kind of true, right? In a normal chemical reaction in our lab, we can't change atoms of one element into atoms of another. We can just rearrange them. So this is true like in lab, like in normal scenarios. But we have nuclear chemistry, which obviously we would not be doing in lab, but nuclear chemistry can change atoms of one element into atoms of another. My best example for you is going to be something like carbon dating, right? We have carbon-14 is a radioactive isotope of carbon, and over time that carbon-14 will decay, and it will change into nitrogen, right? So we can actually see how old something is based on the amount of carbon-14 that it has, which is really cool. But that carbon is changing into a different element. So I like to say number 4 is kind of true. It's true as far as lab goes, but in reality, we actually can do nuclear chemistry. We can do fusion, we can do fission, right? And we can change atoms of one element into atoms of another, which is cool. Okay, so John Dalton provided kind of a foundation. He said, okay, there's got to be something little, and he kind of thought it was going to be like this like solid mass, right? Indestructible little particle, and that is the smallest thing out there. Well, J.J. Thomson started doing some work with cathode rays. So this is his cathode ray experiment. And J.J. Thomson constructed a partially evacuated glass tube. And so what that means is he essentially put it under vacuum and sucked out most of what's in there. So sucked out all the air, stuff like that. And he called this a cathode ray tube. And he found that a beam of particles, which he called cathode rays, aka electrons, right, negatively charged stuff, traveled from the negatively charged end, so from this side, and they went to the positively charged end, called the cathode, right? So they go, they're going from the cathode to the anode, my apologies. And so he said, okay, whatever is in there must be negatively charged because it's being repelled by the negative side. It's leaving the negative side and it is attracted to the positive side. So whatever in there must be negatively charged to be attracted to that positive end. Okay, so he said, all right, so the atoms aren't just these small, hard spheres. There's other stuff in there. There are teeny tiny positively charged or negatively charged particles in this sphere. So he said, okay, John Dalton, it can't look like this, right? There's stuff in there. There's electrons in there, and he didn't know necessarily where they were, so he just said, okay, let's assume that the negatively charged particles are just kind of spread throughout, right? So here's an electron, there's an electron, right? And then everything else is going to be positively charged. So all of this like red stuff, that's going to be positively charged because we know atoms are neutral, so the negatives have to cancel out the positives. So he called this the plum pudding model. You can think of this, I mean, since we're not British and probably nobody eats plum pudding, you can think of this as like the chocolate chip cookie model, right? The cookie is positively charged and it's got a bunch of negatively charged chocolate chips kind of spread throughout. So this was an updated version of the atom, right? We took John Dalton's, we added in our electrons, and now we have the plum pudding model. So another person who did some research on the atom was Millikan. He did his oil drop experiment. And so the oil drop experiment was to figure out the charge. Only one to do some work with the electron. He's credited with discovering the electron, but Robert Millikan is credited with discovering the charge of the electron. So based on J.J. Thomson's work, we knew that there were negatively charged particles, but we didn't know how negative they were. And so Robert Millikan's work was to figure out, okay, what is the charge of these negatively charged particles? So the way that he did this was he performed his oil drop experiment. And so what happens is we have this atomizer here, and so he sprayed oil, essentially, and the atomizer broke it up into a bunch of little individual atoms, and then it went through and got hit by this ionizing radiation. And what the ionizing radiation did was it made those oil droplets charged. So now they carry a negative charge. And so the other key part of his experiment is that on top, he had a positively charged plate, and on the bottom, there was a negatively charged plate. And he said, okay, I can alter the charges of these two plates, this positively charged and negatively charged plates, and I can cause these ionized oil droplets, right? These charged oil droplets to be suspended because they're being attracted to the positively charged plate and repelled by the negatively charged plate. So if he could, alter the charges of these two plates, he could get them to suspend in midair, which is super cool. And so that's what this says off to the left here. By measuring the strength of the electric field required to halt the free fall of the drops, and by figuring out the masses of the drops themselves, and the way that you can figure out the masses is from the radius and the density. So he had the mass of the drops and the strength of the electric field, so he was able to calculate the charge of each one of those drops. And the charge on any one of those drops was always a whole number multiple of this, negative 1.96 times 10 to the minus 19th. That is the charge of an electron. So say maybe there were, two, if this was multiplied by 2 on one of those drops, right, because it'd been ionized twice, essentially, but it was always a whole number multiple of this. So that tells us, okay, if there was only one of those electrons, that would be its charge. So that was really cool. So Robert Millikan is credited with discovering the charge of the electron. Rutherford's gold foil experiment is probably one of my favorites in this one. So here's what happened. Rutherford used this, had a source of these alpha particles. And alpha particles are positively charged. And remember, we're still working with J.J. Thomson's model of the atom, that plum pudding model. And so the plum pudding model says, okay, most of it is positively charged, but we've got these little negative electrons kind of spread throughout here. And so Rutherford took this piece of gold foil and he said, okay, if the atoms are mostly positively charged, then if we shoot a bunch of alpha particles through it, most of them should go straight through. And so what happened is that most of them did. Most of them had little to no deflection. So we shot our positively charged particles this way, and then this is a detector that's used to figure out where these alpha particles hit. And so most of them went straight through, or kind of went off at a little bit of an angle, but most of them went straight through. A couple of them went off at very big angles like this, right? And some of them, even crazier, bounced back. And it's the ones that bounced back that threw Rutherford for a loop, because he's like, why are they bouncing back? Why are they not going straight through? That's bizarre, right? This was an unexpected result. Majority of the particles, like I said, did pass straight through the foil, but some particles were deflected and some were bounced back. And so he said, okay, why are they bouncing back? There must be something in the atom. It can't be very big because most of them went straight through. So, but there's got to be something in the atom that some of these particles are hitting. And it's got to be very hard, it's got to be very dense, and it's got to be positively charged, because these alpha particles are positively charged, and there must be something in the middle that's repelling them. If it was negatively charged, right, the alpha particles would stick to it. And if it was, maybe if it was neutral, then they wouldn't be deflected so much. But it's got to be something very, very small, because not many of them bounced, right? It's got to be hard, and it's got to be positively charged. And so he said, okay, well, it can't be, the atom must not be this plum pudding model, because otherwise they would go straight through. And so there's got to be, instead, the atom must be mostly empty space. That's why most of them went straight through, because the atom is mostly empty space. But there's got to be something in the middle that's causing this deflection, right? And like I said, it's got to be small, it's got to be hard, dense, positively charged. And so he determined that what they're hitting is, in fact, the nucleus. And so this is cool. This totally revolutionized the model of the atom, right? No more were we looking at this plum pudding model, and instead we have, kind of closer to the modern model of the atom, where we have the nucleus surrounded by more of empty space, which we now call the electron cloud, right? So, like I said down here, he concluded the matter must not be as uniform as it appears, must contain large regions of empty space, right? Most of them went straight through, with very small regions of dense matter, aka the nucleus. And what's really cool is that Rutherford was actually J.J. Thomson's student. So he's like, hey, professor, sorry, but your model of the atom's wrong and mine's better, is kind of what happened. But yeah, pretty neat. So then we had the Rutherford model of the atom, something hard, dense in the middle that's positively charged, and the electrons were somewhere around the outside, but it was mostly empty space. They weren't really clear on that, right? So here are, Rutherford came up now with nuclear theory. So nuclear theory has 3 basic parts. The first one is that most of the atom's mass and all of its positive charge are contained in a small core called the nucleus, right in the middle. And when it says most of the atom's mass, these protons are really big compared to the electrons. Electrons are so small. Most of the time in our calculations, we assume they have actually no mass at all, and that all of the mass is coming from the protons just because they are so much larger. It's kind of like, if you Think about the hairs on your head compared to the mass of your entire body. Yeah, they have mass, but it's really, really small. So it's not really changing your mass all that much. The second one is that most of the volume of the atom is empty space, right? That's why most of the particles went through. But throughout there were these tiny negatively charged electrons are kind of scattered around. So we've got small, dense, positively charged nucleus and electrons kind of floating around the outside somewhere. And then the last one is that there are as many negatively charged electrons outside the nucleus as there are positively charged particles within the nucleus. And we call those positively charged particles protons. And for this reason, right, the atom is electrically neutral. We knew the atom was neutral already, so he figured out, okay, if there's these electrons floating around the outside, we must have an equal number of protons in the nucleus so that it balances out the charge. And although Rutherford's model was highly successful, scientists realized that it was incomplete. One of the reasons is, why doesn't the nucleus fall apart? There's a bunch of protons in the middle, right? Protons are positively charged. And if there's a bunch of positively charged stuff right next to each other, why don't they all repel each other and fly away? So what's causing it to stick together? And where's all the extra mass coming from? We had electrons, which we know have a really, really small mass, and we have protons, which have some mass, but there's extra. What is the extra mass coming from? What does that do to? Can't be more protons or more electrons because we know the charges of the electrons, and there has to be equal number of electrons to balance out the protons because we know that the atom is neutral. So it's like, okay, well, what's happening there? There must be something else in there. So there was later work by Rutherford and one of his students, and they demonstrated that there was these neutrons that happen to be in there. There are neutral particles in the nucleus. So that's why the atom doesn't fall apart, right? There's these neutrons that are in there that are kind of acting as blocks between the protons to keep them from repelling each other. They kind of act as like a glue and as like charge blocks, essentially. You can kind of think of them that way. But this accounted for all of that extra mass. So, and they don't have to equal the number of protons or electrons because they are neutral. So we can have as many neutrons as we want, really. And then later, this is just kind of, preview, woohoo. Later, we're going to talk about another one of Rutherford's students, which is Niels Bohr, and he improved even more upon this model of the atom that Rutherford came up with. And he put the electrons into orbitals. So instead of them just like floating around off into nowhere, Niels Bohr organized them into orbitals. But more on that later. We'll get to it. So the mass of a neutron is similar to the mass of a proton. We actually will mostly treat them as being exactly the same. They're that close. So we say, okay, mass of the proton, mass of the neutron, they're about the same. However, sorry, this is cut off. However, a neutron has no electrical charge. That's what this says. However, a neutron has no electrical charge. The helium atom, for example, is 4 times as massive than the hydrogen atom because it contains 2 protons and 2 neutrons. That's what's cut off. Sorry. These are showing up differently on my iPad than they were on PowerPoint. Hydrogen, on the other hand, only contains 1 proton and no neutrons. Quick question, why does hydrogen not have any neutrons? So if you'll recall from the previous slide, right, the reason, or one of the reasons that we have neutrons is to keep the nucleus together, right, because protons repel each other. Well, hydrogen only has 1 proton, so it doesn't need any neutrons. It can have them. We have things called deuterium and things like that, where they have another neutron, or a neutron, and then you could have 2 neutrons if you really wanted to, but it doesn't have to, which is cool. So hydrogen is the only atom that doesn't have to have neutrons because it only has 1 proton. So here are the subatomic particles we've talked about so far. We have protons, we have neutrons, and we have electrons. Protons and neutrons, like we talked about earlier, have nearly identical masses. So here's the mass of the proton, here's the mass of the neutron. So see, they're really, really similar. They're similar to 3 significant figures, and they're still very, very small, right? So these, we essentially say they've got pretty close to the exact same mass. We'll treat them like they have the same mass most of the time. And then if you look, the electrons are way smaller. They're almost 1,000 times smaller than the protons and the neutrons. And that's why we treat the electrons like they essentially have no mass, just because it's so much smaller. But sometimes you'll have to actually use the mass if you're going to calculate numbers of electrons and things like that. But for most of kind of our crude calculations, we'll treat them like they don't have any mass. So here's a summary of that. So we have protons, neutrons, electrons. You have their masses there. We have their mass in AMUs, which is atomic mass unit, and we'll do some work with that. Essentially, the way that works out is that protons have a mass of 1, neutrons have a mass of 1, and electrons will have a mass of 0, is kind of how we treat it most times. Protons are positively charged, neutrons are neutral, and electrons are negatively charged. And then at the end, we have the charge of the electron. So here, we talked about this in a previous slide, right? That was Robert Millikan's work to determine the charge of the electron. And remember, the protons have to exactly equal out the electrons. So if that is the charge of the electron, then it must also be the value for the proton, except now it's positively charged instead of negatively charged. And then again, the neutron has no charge because it's neutral. So elements are defined by their numbers of protons. This is really, really important. The most important number to identify an atom is the number of protons in the nucleus. Okay, the number of protons defines what element it is. So if you were to look at the periodic table and you were to say, okay, I want to figure out what element has 6 protons, you would look and find atomic number 6. That would be carbon. Anything that has 6 protons is always going to be carbon because the number of protons defines which element it is. Okay, so the number of protons in the atom nucleus is called the atomic number, and it is given the symbol Z. And I know that doesn't make a lot of sense for why it should be Z. Just roll with it. It just is. So here we go. This is the periodic table, right? And so like I said, anything with 6 protons is going to be atomic number 6, and that will always be carbon. If you were saying, hey, this atom has 30 protons. Okay, well, that's always going to be zinc. Anything with 30 protons is always going to be zinc. And vice versa, right? Zinc will always have 30 protons. The number of protons identifies the atom. The number of electrons can change. We call those ions. The number of neutrons can change. We call those isotopes. But the number of protons always stays the same. Okay, you can't change the number of protons. If you change the number of protons, then you change what element it is. So each element has a particular number of protons, neutrons, electrons, which are unique to only that element. So again, we have the atomic number, which I said was Z, right? And Z is the number of protons in the nucleus of an atom. Z will also equal the number of electrons, but only for a neutral atom. Okay, remember we talked about earlier that atoms are neutral, and so our protons must equal our electrons. So if we're thinking about zinc again, zinc has 30 protons, so it will also have 30 electrons because it has to be neutral. Kind of like carbon, carbon has 6 protons, so it has to have 6 electrons in order to be neutral. Okay, this won't be true as soon as we start talking about ions, right, where things can gain and lose electrons. But when we're talking about atoms, neutral atoms, the protons and the electrons will always be the same. Okay. And then the mass number, which is the number at the bottom, not on this periodic table, but normally you would have a mass down at the bottom where it says the name of the element there. And the mass number is the number of protons and the number of neutrons. And so I want to make a quick distinction here that there's 2 different things that we'll talk about. So if you were to look on a different periodic table, you would see, like we'll take carbon for example, it'll say 6, C, it'll say carbon, and then it'll have a mass down at the bottom, so like 12.011. Okay, and so this is what it might look like. This number at the bottom here, this is what we call the atomic mass. Okay, and that is the average mass of the element. That is different from the mass number. Okay, and I want to make this really clear. The mass number is the total number of protons and neutrons. And so this will have to be a whole number because we're adding together other things that are whole numbers. This is kind of like when we were talking about significant figures and we were talking about counting items, right? You can't have, 1.02 protons. It doesn't work out that way. So the mass number is this atomic mass rounded to the nearest whole number. So for example, carbon's mass number would be 12. Okay, mass number and atomic mass are not the same thing. The mass number will always be a whole number, and the atomic mass will always be a decimal number. Okay, so be very, very careful there. That is a trick question, but it's not intending to be a trick question. It's kind of just a particular question. Okay, so we have this isotopic notation that we can write it. So this X is the chemical symbol for the element. So if we're thinking about carbon that we were working with on the last slide, right? So there's carbon. So if we were to write this for carbon, our chemical symbol would be C for carbon. The mass number goes on the top. Okay, so the mass number is the number, the atomic number plus the number of neutrons. But it's also this atomic mass, which has been rounded to the nearest whole number. So 12.011 rounds to 12. The number on the bottom is the number of protons. And so that will be this atomic number here. So that'll be 6. Okay, so again, this is the element, this is the element symbol. This is the mass number. And this is the atomic number. And if you ever needed to find the number of neutrons, you can always just take the mass. It's kind of like set up for subtraction. You can take the mass minus the atomic number, and that will give you the number of neutrons. Okay, because neutrons plus protons equals mass, if you were to go back up that way. All right, so let's try this out. So if you've got a periodic table handy, go ahead and find it now. There's also one on Canvas that you can pull up. So go ahead, if you need to go find it, pause here and then move forward. All right, an atom has 14 protons and 20 neutrons. So I want you to figure out the answers here. So an atom that has 14 protons will be atomic number 14. Okay, if it's 14 protons and 20 neutrons, the mass number, remember, mass number is always protons plus neutrons. These are how we abbreviate protons and neutrons, P plus because protons are positive, and N0 because neutrons are neutral. So mass is always going to be protons plus neutrons. So 14 plus 20 gives us 34. And so then you have to figure out, okay, what element is this? So remember, your elements are defined by the number of protons. So we go and we look, okay, what is atomic number 14 on the periodic table? And we see that is silicon. Here's another one. So go ahead and pause so you can work through this. Okay, an atom of zinc has a mass number of 65. How many protons are in this zinc atom? Now remember, it doesn't matter what the mass of the atom is to figure out the number of protons because the protons define the atom. So we look at zinc on the periodic table and we find that zinc is atomic number 30. Therefore, zinc has 30 protons. And then it asks how many neutrons are in this zinc atom. Okay, well, it's got a mass number of 65, and we know that it has 30 protons, so the rest of the mass must be coming from the neutrons. Therefore, it has 35 neutrons, because we'll go 65 minus 30 gives us 35. And then it says, what is the mass number of a zinc atom that has 37 neutrons? Okay, well, we know the mass is always, right, mass number is always protons plus neutrons. So the protons never change. That's always going to be 30 for any atom of zinc. And this one has 37 neutrons. Therefore, its mass number is going to be 67. Okay? And that's it for this set of slides. So go ahead and work on this. Check out that Chapter 1 lecture worksheet. You can do kind of the beginning of it, that neutral atoms table. And then I will see you guys all next time when we continue Chapter 2.